Graham, you didn't even participate. Wow. Okay. So let's plug that stuff in our calculator, please, if you have not already done so, and come up with the work done by the force of gravity on the box while it's on the inclined plane. Again, and also remember, you are pushing a sine, cosine, or tangent button. So what does you need to make sure you have done on your calculator? Degree. You need to be in degree mode, okay? I can barely see. Mm-hmm. Bernie, are you for sure? The second and the down arrow changes the contrast. I did not know that. No, that's dope. No, it can't hold it down. No, this second and then you hold down. I have contrast. You're still holding down the second. Okay, so I'm not in the right mode. Anyone? Madison, you got it for me? All right, well, let's hear that number. Well, I think this is one of our final answers, right? Yes. Yeah, so let's do sig figs, please. How many sig figs should we have? Very good, 3. Joules, very good, okay? Very good, that is the correct answer. Negative 22.0 joules of work done, okay? Now, what's that negative sign mean? Down. Down, okay? I believe I had a decimal point after that. Yeah. Okay, questions about how we came up with the work done by the force of gravity? Do we follow that whole process? Let's run back through real quick, a little review on how we did all this. Gosh, that looks amazing. Look at all that. That is beautiful. Okay, so we start out with our picture. We understand that the final velocity of part 1 is the initial velocity of part 2, okay? We know that we have to find the displacement of the box up this ramp because that is part of the formula for work, okay? That's something we don't know. We don't know what the displacement is, so that's the thing that we're after, right? We can't do any energy stuff about this second part of the problem because there's friction there. And we know that energy is only conserved when there's not friction, correct? So if we know that the box comes to a rest, then we know the final velocity. If we are able to figure out what the initial velocity of the box is on the ramp, then we've got the initial velocity. So all we needed was some other method to get a third kinematic variable. And once you had that third kinematic variable, you could easily calculate the displacement using your kinematic equations, right? And since this is going to be a box on an inclined plane, it makes sense that we can do forces. So we did our F-net statements to figure out what the acceleration of the box on the inclined plane was. So all this stuff right here, where we're doing energy, this is us figuring out what the final velocity of part 1 is, which is also the initial velocity of part 2. Okay, so that's that right there. Then we do our F-net statements so that we can figure out what the acceleration of the box is on the incline. And once we figured out what the acceleration of the box is on the incline, then we have 3 kinematic variables. And if you know any 3 kinematic variables, what does that mean? And then what? Very good. Be left with one happy physics student, okay? So we took our displacement then, we plugged that into our work formula, and we solved for the work done by the force of gravity. Yes, Graham? All right, so that's the part 1, okay? Now we need to do part 2 of our question here. Actually, I think that was part B. That was that letter B. We need to do part A, the maximum height up the ramp that the block travels, okay? All right, so any ideas on how we can do this? What do you think we need to do next? Sokadoa? Well, I think I need you to elaborate a little bit more for me on that one.
The sine of the height equals, or the sine of this theta equals the height over the displacement of the hypotenuse, which we already found, which is 2.655820887.
All right, so we know that the sine of theta is equal to the opposite over the hypotenuse. And if you go back up and look at our picture here, okay, we just figured out what this displacement is, right? So that's going to be the hypotenuse of our triangle, correct? And we know what the angle of the incline is here, right? So if I'm trying to find the maximum height up the incline that the box moves, I'm looking for the opposite side, correct? So I need to rearrange my sine of theta equation to solve for the opposite side. Okay. So I'm going to say that this was the H max and that this was our displacement here. So I'm going to multiply. I'm going to say that the maximum height then must be equal to the displacement times the sine of theta. And remember, this theta is not the theta from the work equation. This is the angle of incline, all right? So let's plug that in. What was that displacement value again, Shivam? All right, so type that into your calculator, please. How many sig figs should we have here? 3, very good. All right, Graham, what'd you get? Okay, raise your hand if you agree with that.
I got something different.
Fantastic, that's correct, Graham. Next question. A ball with a mass of 0.360 kilograms is dropped from a height of 1.2 meters above the top of a faced vertical spring. It means the spring is pointing upwards. The spring constant is 350 with a decimal point Newton meters. What is the speed of the ball when the spring has been compressed by 5 centimeters? So I'm going to give you a moment to write that down, and I want you to attempt to draw the picture that's being described by the problem. This is an important part to being able to solve these questions correctly, is for you to be able to generate the picture without me, okay? Okay, so what I have here, I've split this picture into 2 different scenarios, okay? So the first one, where the spring is not expanded, all right? It is at its equilibrium position, okay? The ball is then going to fall down, and it's going to compress the spring by 5 centimeters, okay? So this is the picture of the spring once it's already been compressed, and we'll have the ball will, at this point, be sitting on top of the spring right there, okay? Which means that from here to here is the 5 centimeters. Okay, so now this is an energy problem, right? So what 3 things do you have to do?
Initial, final, and 0 line.
Very good. We need initial position, a final position, and a 0 line. Okay, so you have a couple of options. You could set this as a 0 line.
No.
We could set this.
Let's set the green line as the 0 line.
Okay, that or that. Now, it really doesn't matter what you pick. You just have to be consistent the whole time, okay? So what do you want to be your 0 line?
Middle line.
The green one here? Yeah. Okay. All right, so we've picked our 0 line, and now what else?
Initial should be like the what if the
Ball.
The ball. So
Yeah.
the ball went before.
Okay. Shh. We got the initial positions, the ball at the top. Where's the final position?
The ball on top of the spring.
Okay, the ball when it's on top of the spring. All right. So now that we have those 3 things done, what do?
Mechanical energy.
Yeah, we need to use the conservation of mechanical energy formula. Okay.
There's no friction.
So very good. So we're going to say mechanical energy initial is equal to mechanical energy final.
Did you ever put the video
What's
out?
up? We don't do that in this class.
When the ball's going down, but does the velocity change constantly because it's being absorbed by the spring?
Well, the ball is accelerating on the way down, so the velocity would change. But we've actually set a stopping point. We said once the spring has been compressed by 5 centimeters, we want to know what the velocity is at that exact instant. So, of course, if the spring continues to compress, the velocity would change even more. And then once the spring starts going the other direction, it would. Yeah, well, that would be a calculus-based physics. We could actually calculate what the change in velocity would be at any moment in time during the compression of the spring if we did calculus. But we're going to stop it at certain moments for this class. All right, so let's look at the ball up at the top. And what are all of the kinds of energy that the ball has at the beginning?
Potential. Kinetic, it does it because it's being dropped.
Very good. So Shabam says it's not going to have any kinetic energy because the initial velocity of a dropped object is what? 0. So no kinetic energy. But Brady says it's got what kind of potential? All right. So it's got initial gravitational potential energy. Anything else? That's it for the beginning. Okay. Now let's look at the end. When the ball is at the final position, what do you say? What kind of energy?
Potential energy due to gravity because it's touching the 0 line.
Very good.
It's going to be kinetic because it's still moving.
Okay.
Yeah,
There will be.
Is there potential elastic?
Yeah, because it ran into a spring, right? Okay, so it's going to have elastic potential energy final. Okay, and now what do I need to do? Expand those. All right. Because you guys chose that the middle line there to be the 0. Right. So we've got, what's the formula for gravitational potential energy?
MGH.
Okay. And what H? The initial height, right? Okay, what's the formula for kinetic energy? What V? What? Final. Okay, and what's the formula for elastic potential energy? Kx something squared.
I don't have much sheet.
And what X? What X? Final, okay? Because we're on the final side of the equation, right? The displacement of the spring from the equilibrium position. Okay? All right, so let's go ahead and start plugging this stuff in then. What am I trying to solve for? Which velocity? Final velocity. Very good, okay? So tell me what I need to do first. Okay, so I'm going to subtract this term right here to the other side of the equal sign, all right? So I've got my 1/2 m v final squared is equal to mg h naught minus 1/2 kx squared. Okay? What now? Okay, let's multiply every term here by 2. And what else? Divide everything by mass. And then I need to take the square root. Very good. So we're going to say then that the final velocity is equal to, now anytime you introduce a radical, plus or minus, and we'll have g times h naught minus k times x naught squared. Did it ask for speed? Yeah. Okay, so good call, Graham. We actually don't need the direction here. Okay, that's the Molbux right there. Yeah. Yeah. Oh. Okay. All right. Now, let's go through and plug that stuff in. So V final is equal to the square root of 2 times 9.81 meters per second squared times. Now, what's the initial height of the ball? Okay. Well, that's 1.20, but we need our, remember H, the height in potential gravity is the height above the zero line.
1.20 plus
0.05.
So 1.25.
Okay. Very good. So that's going to be 1.25 meters minus, now, what's the spring constant in this problem? Okay, 350 newtons per meter times. All right, now, did I put the wrong x value in there? Hold on. Yeah, that's supposed to say final. This right here is supposed to be the x final, not initial. And this is not an issue, just a wrong subscript there. Okay, Sean? Sure. You need to start doing that before class. Okay. Yeah, times h naught. Now, x final. Okay. The displacement of the spring away from the zero line. What's that going to be?
0.05.
Well, which way? Yeah. Okay. So our you guys chose your zero line, and let's just confirm. I'm just making sure here. Okay. You guys chose for this to be your zero line, right? Okay. So if this is the equilibrium position, how much was it displaced to the final? Right. -5 centimeters. Okay. So that needs to be -0.05 meters, right? -0.05 meters, and then we square that term, right? So does that negative sign matter for us there? No. Okay, so go through, type that in. Please don't forget to take the square root. Yeah, the zero line that you guys chose is right here. So the equilibrium position of the spring when it was not compressed is up here. That means it had to move down by 5 centimeters. That's why it's -0.05 meters is the displacement away from, or yeah, away from equilibrium.
Anyway, so it doesn't even matter.
Right, but you still need to have that in there. What now? No, -0.05 squared. The x term is squared.
All right, we got the same thing.
Because that's 5 centimeters, and you have to use meters. Okay, so who's got the final velocity for me?
Everyone got different. One second. No. I got 4.70047.
All right, so with the right number of sig figs, what is that?
4.7.
Thank you.
And there's no negative because we're just finding speed and not direction.
Fantastic. Okay, so 4.70 meters per second is the correct answer. Now, when I did my problem, I did not choose the same zero line as what you guys chose. Okay, when I worked it out for myself, I chose the equilibrium position of the spring to be my zero line, but I got the same answer as what you got. Okay, so it doesn't matter where you put your zero line so long as you stay consistent. The key to this problem was when we decided to use 1.25 right here. Okay, you needed to know that the height initial is in reference to your zero line. So we had to account for the 1.2 meters and the 5 centimeters extra above the zero line. If we had put this in wrong, then you would have gotten that problem wrong. Okay, Graham?
4.7004. Graham, did you divide by mass on the second one?
Oh.
What do we divide by 0.302?
Yeah, there's a mass under there.
Yeah, I forgot. My B.
See, that's why I just divided by mass at the end instead of canceling the mass.
You're smart.
All right. Questions? Okay. Let's get this next section of notes down, please. We are now moving into a situation where we will be able to work with friction and energy at the same time. Okay. So let's write that down. Mechanical energy with friction. Okay. So the work done by friction is actually going to be equal to the change in mechanical energy. And we know that anytime I have delta, the change in, what does that mean?
In final minus
Yeah, final minus initial. So I can say then that the work done by friction is equal to mechanical energy final minus mechanical energy initial. Okay?
We still can't do that homework. We still have,
I know. We're trying to get there as fast as possible. I know. All right, so again, since this is an energy problem, you must do those same three things. You have to choose a zero line, you must choose an initial position, you must choose a final position. Work done by friction will be defined as any resistive force, okay? The work done by any resistive force. So obviously friction resists motion, so that's going to count. But then there would be anything else, such as if you have a bullet that is entering a tree, okay? The tree is going to be pushing back against the bullet. That's a resistive force. If you're applying the brakes on a car, the brakes are a resistive force. A resistance over the top of a vehicle or a plane or a skydiver, whatever, is going to be a resistive force, okay? Unless I tell you otherwise. And then friction, of course, we know has its own formula. The friction is the mu times the normal force, right? So you could expand that. So we know that work is equal to force times displacement times the cosine of theta. So we end up with this resistive force here. The work done by a resistive force is equal to the change in mechanical energy. This could be expanded further if we had a mu and a normal force, right? So we could say mu times normal force, and normal force, if it was on an inclined plane, is what? Mg cosine theta, right? So this could be mu times the normal force times d times cosine theta equals delta me, I would, okay? Or we could expand that and say mu times m times g times cosine of theta times d times cosine theta equals delta me. And I'm going to call this theta 1. I'm going to call this theta 2 because theta 1 would be the angle of incline, but theta 2 would be the theta in reference to the work formula, which is the angle between the force doing the work and the displacement vector. Okay, so make sure that you wouldn't plug the same angle in for both of those. Well, we don't know what kind of mu we're talking about here yet. So I'm just saying mu. Well, then, okay, we can do that. But what if we're talking about a tire that's rotating? And then it would be static. So it's really kind of open.
Yeah, when don't your tires slide?
Only if you like stomp on and you're skidding, then it would turn into kinetic friction.
What about the brake on the tire?
That itself would be a resistive force applying in the opposite direction to slow the vehicle down. Good job, Graham. Okay, so did you guys get this yesterday? Yes? Awesome. All right, then we can move to the next part. No, I do. It's just this is y'all's lines. This is y'all's lines in time, not his. Okay. So 3 things about the direction of the force of friction, okay? And these are things that we should already know because we've been dealing with friction for quite some time now. But obviously, it's going to oppose the motion, which makes that a resistive force. When we're talking about work done by friction, we said that is any resistive force. So obviously, friction counts. It is always parallel to the surface. Okay, friction's not going to be perpendicular. And it is independent to whatever the applied force is. Because remember, friction is based off of normal force, not the applied force. Yes. Do what? No, I'm good. Thank you, man. All right, so the force of friction is therefore always opposite or 180 degrees away from the displacement of the object. There can be some exceptions to that, but we're not going to talk about them in this class. Okay, so we know when there's no friction that mechanical energy initial equals mechanical energy final. So if we're looking at our formula here, we know that the work done by friction is equal to the change in mechanical energy. So that'd be mechanical energy final minus mechanical energy initial. But if the work done by friction is 0 because there is no friction, then we would have 0 equals mechanical energy final minus mechanical energy initial. We could add mechanical energy initial to the other side, and we would get our conservation of energy equation. Mechanical energy initial equals mechanical energy final. All right? So the formula for mechanical energy when there is friction is actually the same as the formula with mechanical energy without friction. It's just that's a special situation when friction equals 0. So, and then finally here, because theta is always 180 degrees and the work equation has cosine of theta is -1, that means the work done by friction will always be a negative value. Yes.
Okay, so let's say there's no friction, but I'm pulling a box this way, Brady's pulling a box this way, but I'm pulling it harder, so it's moving this way. Does it still like count as a friction? Or
There would be a resistive force. Yeah. A resistive force. Yeah. We could say, now I say I'm used to calling this work done by friction, but really technically should be saying that that's the work done by a resistive force. But it's just so much easier to say work done by friction. So, yeah. So let's look at an example here, okay? How far does an object slide when kicked to the left with an initial speed of 2.5 meters per second? The coefficient of static friction is 0.11 between the object and the ground.
Yes.
So when that says how far, what are we asking for? The displacement. Very good. You can't win them all. Okay, so now it says it was kicked to the left with an initial speed of 2.5 meters per second. So what do we know? Yeah, we know our initial velocity is negative 2.5 meters per second. Now notice, they gave us a speed, but they also then told us the direction. So that turns it into a velocity, right, which is a vector quantity. And then we've got our static coefficient of friction is 0.11. Okay.
Do you know velocity final is 0? It's going to come to a stop. And that's where your distance is.
True. Because there's friction, yeah. So that's stealing energy the whole time. So the object should come to a rest. All right. Now, we only have 2 kinematic variables, right? So we can't use a kinematic equation as of right now. So what do you want to do? We could do an F-net statement, and then what would that hopefully get us? That would get us acceleration. Then we would have 3 kinematic variables, and then we could solve for the displacement using a kinematic equation. But since we're in the work and energy section of our notes, we should probably use work and energy to solve the question. So what do you think we should do then?
Mechanical energy final minus mechanical energy. Or do the 3 things. Initial, final.
Okay, we need to draw a picture first, so let's do that. Okay, let's say that we kicked the ball, all right, and we kicked it to the left, and we know that the initial velocity was 2.5 meters per second, and the ball is going to eventually be over here.
I was gonna say, oh, it's rolling, so it's set.
No, if I like kick a box or something and I cause it to slide, then that would be kinetic friction. That would be applying. And remember, the only difference between static and kinetic. Static friction is always larger than kinetic friction, so it would change, you know, the work done by friction by just a little bit.
Oh, W, the work with friction equals delta ME. Delta mechanical energy.
Okay, cool. So this is the one we want to use here then, okay? The work done by friction is equal to the change in mechanical energy. Yes, we shall. So what's the formula for work done by friction? No, the formula for work.
Static friction times displacement plus cosine.
Very good. Yes.
If you look at the part where of the formula that we're talking about friction, it specifies kinetic friction.
Okay, now look at your or the change in mechanical energy. So, if we're going to do anything that has to do with energy, what do you have to do? Those 3 things, which is what? Initial and final zero line. Where do you want the initial position to be? Okay, where it starts. Where you want the final to be? Where it stops. And where do you want your zero line? The ground. Okay. Because the ball's going to, if I kick a ball, then it's going to rotate, so it means one point on the ball would be touching the surface at any given moment in time, so that's why it's static. Yeah, friction force, yeah. Okay, now, what kind of energy do we have? We know that delta means final minus initial, so let's focus in on the final section over here first. What kind of energy does the ball have at the end? No energy. It came to a stop, so there's no kinetic. It's sitting on the zero line, so there's no gravitational, and it didn't run into a spring, right? So no energy at all at the end. So we can say 0. If you put the zero line at the bottom of the hill, yeah. Okay. Now let's talk about the energy that it had over here at the beginning. What kind does it have? Kinetic energy. Okay. So what's the formula for kinetic energy? Okay. Now what is it we're trying to solve for here? The displacement, right? So what do you want to do? Oh, cool. Now let's look at something before we start dividing by friction real quick. My given information over here, I don't have anything to do with friction, right? What do I actually have over there? I've got mu. So I need something to do with mu in my equation. What do I need to do? Yeah, we need to expand friction. Okay. Yeah, mu times the normal force times d.
Oh, mu s equals.
Yeah, times the cosine of theta. Now, do you know the normal force? No, we don't know the normal force. What can we do? Okay, we could do mg cosine theta. That's the normal force when it's on an inclined plane, all right? Now, imagine that our inclined plane has been dropped so that the angle of incline is 0. What's cosine of 0? 1. So that would just be multiplying mg by 1, right? So just mg, okay? So we're going to expand again and say mu s times m times g times d times cosine theta equals, now we can put all of our energy stuff back over here, 0 minus 1/2 m times v naught squared. What do you notice? Very good. Everybody brought mass to the party, so we can get rid of that. Now, let's solve for the variable that we're looking for, which is displacement. So I'm going to divide by mu s, g, and cosine theta on both sides.
What do you say that?
Adam, I told you something you could say. Isaac said, I was thinking about this thing last night, and I told him to say, I was just thinking about that. You should have been doing your speech. But he wouldn't say it.
All right, now let's plug in our stuff, okay? The negative here is on the outside, okay? It's 0 minus whatever this stuff is. So the top is always going to be negative there, okay? That makes sense because the object was kicked to the left, right? So it should come out with a negative displacement. So do your 1/2 times the initial velocity squared, and then divide it by this stuff on the bottom. Slap that negative sign in front of it, and give me an answer, please. Now you have to click the notifications bell if you want notifications when I upload a video. So I think at the end of my videos, I'm going to start saying, ring that bell, down below. And there you go. Smash that like button and ring that bell for me. Really helps me out. All right, what do we get? And how many sig figs should my answer have? 2. Very good. So who's got it? All right, Garrett, what'd you get? What did I say about that? There you go. Okay, negative 2.9 meters. Raise your hand if you agree with Garrett. Yeah. No, displacement is a vector. Distance is scalar. Okay. All right, Graham agrees. That's a good endorsement. All right, good job. Looking good there, Garrett. Okay, and then, of course, box your answer. Fantastic.
Are we finished?
We are finished for right now. All right. Now, a 2.0 times 10 to the third kilogram car starts from rest. What's that mean?
0.
Velocity initial 0. Very good. At the top of a 5.0 meter long driveway that is sloped at 20 degrees with the horizontal. If an average friction force of 4.0 times 10 to the third newtons impedes the motion, what is the speed of the car at the bottom of the driveway? All right. So I want you to draw the picture that this problem is describing on your own, and then I'll draw mine in just a moment. Yeah. All right. So let's see here. What did they ask me about? Yeah. So which speed, or yeah, velocity or speed final, right? Velocity final. We don't really care about direction here, which is why it doesn't matter which way you drew your driveway, because it didn't ask for velocity, it asked for speed. That's a scalar, so it really doesn't matter which way your car is going down the driveway. Right, Cassie?
It just throws me off.
Okay, so what do you want to do? Okay, well, we could write it down. Let's just talk about it, though, so I don't use up my screen space here. What do I know? I know my velocity initial is 0. I know my displacement is 5 meters. Yeah, I would need one more kinematic variable if I was going to find the final velocity, right? Any ideas of how I could get that that third kinematic variable so I could use my kinematic equations? What could I do, Garrett? Yeah, I could do my F net statements, and what would that get me? Very good, Vinay. That would give me my acceleration, okay? But we're not going to do that, okay? Because we are in the work and energy section of our notes, we're going to use work and energy to solve the problem, because there could come a day when I ask you a similar question like this, and I say, solve this using work and energy only. And then you would have to do it that way. And if you haven't practiced it, that would be bad for you, right? So what are we going to do if we're going to do a work and energy problem? What three things do we need to do? Okay, we need an initial position, we need a final position, and we need a zero line, right? Where do you want the initial position to be? Okay, where the car is at the top, okay? All right. Okay, so we've got those three things. Now what are we going to do since this is an energy problem? What's happening?
We can't do the conservation of mechanical energy or friction.
Right, so what are we going to do then?
Do one of those other two, right? The ones with friction, which are...
Oh, mechanical energy with friction.
Yeah,
The WF.
what's that? Yeah.
Is any resistive force. So
Okay.
that equals friction times D times, or lever arm times cosine of theta.
Well, not lever arm, because that's for torque only.
Oh, then that's the distance.
Displacement.
Displacement.
But what's the work done by a resistive force equal to? Yeah, delta ME. Okay. All right. So what's delta ME mean?
That means
Say it again, Sean. Very good. The change in mechanical energy. Okay. So that's going to be mechanical energy what? Very good. So the work done by a resistive force is equal to mechanical energy final minus mechanical energy initial. Okay? So let's go ahead and expand with what Cassie said here. Our work done by a resistive force. What's the equation for that?
friction times displacement times cosine of theta.
Good. Okay, so we're going to have our friction. Now, what kind of friction is this going to be? Static, because it's the wheels, right? Okay, so static friction times our displacement times what? Cosine of theta.
Why is it friction and not before?
Well, friction is a force. Yeah.
Do we have to do that magic angle stuff?
Magic angle.
To determine like the car angle. It's not the one with the...
I imagine we're going to have to use an angle at some point in time here.
No, I think he means, would you use something other than 20 degrees?
Perhaps, I don't know. I'm not there yet. Okay. Now, let's talk about our energy. So, when the car is down here at the final position, does it have kinetic energy? Yes, it does. Does it have elastic energy? Does it have gravitational potential? No. Okay, so what's the formula for kinetic energy? Okay, 1/2 m. What kind of V? Final squared. All right. Cool noises, Graham. Good. It's good. Okay. I'm going to move this up a little bit so I got some space. Minus. Now let's talk about what kind of energy did it have at the beginning. Okay, it had gravitational potential energy. What else? That was it, right? Because it said it starts from rest, right? So no kinetic. And did it take off from a spring? No, so no elastic, okay? So we're going to put, what's our formula for gravitational potential energy? What kind of H? Very good. You're welcome. Okay, so now we can start playing around with this, right? What is it? Which variable are we trying to get here? Velocity final, right? Okay. So what do you want to do?
Well, let's add. We go ahead and cross that M.
You can't do that.
Add the mg type thing, the thing from mechanical energy.
Okay, we can add the gravitational potential energy one to the other side. All right. So I have my frictional force times my displacement in the x-axis times my cosine of theta plus mgh naught equals 1/2 m v final squared. Now, I want to kind of look at the work done by friction, more specifically the cosine of theta term real quick, okay? Remember that theta comes from the work formula. It is not the incline, okay? So remember, this theta right here, by definition, is the angle between the force vector and the displacement vector, right? So let's come over here and look at our deal. Now, since we're talking about friction, okay, which way is the friction force vector pointing? Up, right? That's pointing up the incline, okay? And which way is the displacement of the car? Down the incline. So what's the angle between those two things? 180. What's the cosine of 180? -1, okay? It's -1. So what I want to do then is we're gonna turn this right here into -1. Does that make sense to everybody? So I'm gonna go ahead then and flip these two terms right here around. I'm gonna say mgh minus fsd. Does that make sense to everybody? Okay, so. Yeah, if I've got 180 degrees, cosines always refer to the x coordinate, and so over here, the x coordinate is -1, and the y would be 0. So cosine of 180 is talking about -1. Okay. Other questions? All right. So we still can't cancel out mass because that's not in every single term. Okay. Has to be in every single term in order to do that. All right, now I'm still, again, trying to isolate my final velocity here. So, okay, we could multiply everything by 2.
Divide by mass and then take square root.
All right, so I'm going to say my final speed, remember, because I don't really care for velocity here. It's going to be the square root of 2 times g times h naught minus 2 times fs times the displacement in the x-axis divided by mass. I see a problem. Do you see a problem? Let's go through the information that we know. We know the mass of the car, but do we really care about that? No, we don't care about that. So do we know what 2 is? Do we know what little g is? Do we know the initial height of the car? No, we don't know that. Okay? We know the displacement of the driveway, but we don't know how high the car is above the 0 line, right? We need this. Very good, Isaac. we need to figure out what that height is. So I'm going to let you do SOHCAHTOA real quick and get a height for us. And actually, we don't even have to have an actual value. We could just plug in the equation that you would come up with here if you want to, right? What would we pick? Sine. Okay, so how would you solve for h naught? What would that be? Okay, so that'd be hypotenuse 5 times the sine of 20 degrees. So we could actually just take that and substitute it into our formula instead of h naught, right? I guess we do have to care about the mass of the car still because it's over here. We didn't actually get to cancel it all the way out. Wah, wah, wah. Okay, so go ahead if you haven't already and begin typing all that stuff into your calculator. What? Oh, well, Graham has one. You sure? Okay. All right. Everybody got it, or are we still wrapping up the calculation? I'll give a few more seconds to get it typed in. 3.7 what, Garrett? And everybody agrees with that value? All right. Then I won't fight it. Okay, does that make sense to everybody? Now you understand, I hope, that when we first talked about this problem, there was an alternative way of solving it that was proposed, right? An alternate method. Would that method give us the same answer? It should, okay? If we had done our FNet statements on that car, figured out what the acceleration was with using forces, then we could use kinematics to figure out what the final velocity is, right? I invite you to take the next 3 minutes to do that. Which axis do you care about? Okay. And then there would be a force applied as well. What's up? Is what? You're supposed to have that memorized, Gary.
Force of the plane is when you do something. Oh God. I don't want to be a business guy. You don't do what you just did. You don't care about anything or anyone else's. Act like you know everything and then get half the questions wrong.
Wow. Holy cow.
I'll let Josh, he's my bro, but he gets on my nerves a lot with how much
I'm so gonna have to edit.
bloopers.
This is horrible.
Friendly bastard.
It don't sound friendly to me.
It's like one of those things where they have big groups of people, you know? It's like the business host on like the boss or whatever, everybody laughs and says, and then you get fired. And oh, we're gonna have to use the one.
You know what the formula for normal force is on an incline?
Never mind.
All right. So what's the acceleration then?
Oh, we have the static friction. Crap. I think I know what to do.
Oh wait, yeah, that's true.
Whoa. Mess me up, bro. You got that on the board, then wait, where you're on the board that controls with you? Where you messed up, you control.
Yeah, I forgot we had it too, Brady.
Yeah, I wrote that too. And I was like, okay.
Did that work?
9.66096.
Anybody else getting this?
I got it. That is right.
I don't want miles per
That
hour.
is right. Okay, so like, okay, let me plug that into this other equation and see if that's actually times 2 is 5. Take the square root of that. I got 9. Okay, I don't know what's going on. Penny, what'd you do?
I typed it in. Did you get it, one? Yeah, so 3.7. Yeah, cool. Awesome. There it goes. Love it when a plan comes together.